can undergo SN2 reactions with methyl and primary haloalkanes, and alpha haloketones, and alpha haloesters. So we're looking at the enamine to be the nucleophile, right? So let's try this. Yeah, enamine. And let's give it that. Our nucleophile is going to be here, right? Luckily, this is symmetric, so we don't have to worry about two different possible nucleophiles, right? Our electrophile, well, to find our electrophile, let's see if we can find a leaving group, because we don't have like a normal, like we don't have carbonyl to attack, where the leaving group is sort of, not really leaving group, but you know, we have pi electrons to kick up. I mean, we do have pi electrons, but they like to be kicked up to nitrogens and oxygens, things that are comfortable with lone pairs, right? Carbons, not so comfortable with lone pairs. So this looks like a pretty good leaving group, yes? So that is going to be our electrophile. So we do an SN2 reaction, attack, kick off, and we get this, this arrows come from where the electrons come from, so we're going to draw that from the pi bonds that we're breaking, right? And we're going to, I could just draw the product like this and then do some resonance, but once I draw this product, I'm going to have a positively charged carbon, right? That's not going to be happy. So I might as well just do this step right now. Give us full octets so that our nitrogen is positively charged, but hey, you know what? At least everybody's got an octet. That is horribly disfigured. 1, 2, 3. So 1, 2, 3. 2 and 3 have the double bond between them. 1 is connected to our nucleophile, electrophile, nucleophile, connected, and that. So now, and okay, we've got that. So, then we're going to add HCl, H2O. So HCl in water. And anybody remember what we can do? Can we do this to any amine? I think we can do this to any amine. What do we do when we've got acid and water around? Here. What might we end up doing? So water can be a nucleophile, right? Whenever we've got an ester and we kick off the mostly alcohol-looking part to turn that into that whole thing into a carboxylic acid, water's the nucleophile, right? If water's a nucleophile here, we end up look at it. There. We do this, and we're gonna get that. Eventually we can do some protonation things, and we can turn it into this, at which point we can go, hey, you know what? What if we just did this? And then eventually we also deprotonate that afterwards. And we can get, oh God, what is happening to the master hexagons? There we go. And then when we kicked off this thing, we ended up with, okay, fine. We'll protonate that before we kick it off. Yeah. We'll protonate that before we kick it off so that we end up with that. And then because this is an acidic solution and this is pretty basic anyway, it's probably going to go ahead and go, hey, I would rather, I'm going to end up hanging out like this anyway. But this is just the stuff that went away. This is what we ended up, this is our product, right? Yeah? So it kind of makes it look like using this, enamine, is a way to almost protect a carbonyl or like define like which in a, it's like a definitive way to do a crossed aldol reaction, sort of, right? I mean, because we could do this with a carbonyl as well. This is something do we decide this? Does an enol do this? Yeah, an enol does this, yes.
Where did the hydrogen that's bound to the nitrogen come from?
Oh, acid. I just added this later because I had it like...
And if it's an acid, why is there only the OH?
Because, so let me do all the steps in this because I'm being lazy and that is confusing. Being lazy only works if it's about things that we don't care about, but we do draw lots of mechanisms. So let's do this the right way. Good call. We end up with N with a lone pair. We end up with O, H, H plus, and we have that. Then we're going to have some water conveniently come in and go, hey, I would love to have that hydrogen. Can I have it? And it's like, yeah, sure, you can have that. And in what could be an entirely different step, because it's totally disconnected to this, but could also be in the same step because it doesn't really affect that. Wait. Oh, good. I have the camera moved so it sees all this. We can have H2O each, H3O plus, and we can go, hey, I have a lone pair, and you know what lone pairs love to do in acidic solution? Pick up hydrogens. So this guy gets rid of a hydrogen, this guy picks up a hydrogen, and we get that. Then we can go, hey, you know what? I really love forming double bonds, so how about you just get the heck out of here? And we would kick off. we kick off. Oh no, no, hexagons. Don't leave me in my time of greatest need. That and this. And then we go, oh hey, this is an acidic solution. So this and amines are basically going to be protonated in acidic solution because, well, their pKa's are, God, why don't I remember this off the top of my head? Not the pKa's, not amines, the pKa's. The pKa's of protonated amines, right? Because when we talk pKa, we need to be talking about the acid. So, not the pKa of this, because that would be trying to take away the hydrogen it already has, which is not easy. The pKa of this guy's protonated version is such that if you're in an acidic environment, you're going to end up forming this pretty often. And then let's do that was supposed to be a 2, but it got away from me there. All right. So this guy goes, hey, can I have that? And it's like, yeah, sure, you can have that. And then over here, we end up with a water that's like, hey, you know what? Can I have this proton? And it's like, yes, sure, you can have that. I'll just go be an uncharged ketone. And we get this. Yes? Less confusing? Cool. Sorry, shortcuts. All right, so basically, it kind of makes it look like these guys, or at least, what do we start with? In just a second and all. And the thing I don't like drawing. These guys can sort of be like protecting groups for a ketone, kind of, right? Like it's sort of like a protecting group, except it's also sort of like helping the reaction happen too, because it's forcing it to be the enamine. It's forcing it to have this guy be in this, have the double bond here, right, instead of here, because, well, that guy's not having it like an oxygen would. Yes?
I don't know if it's a big deal, but it says primary haloalkanes, and that's an alkene. And wouldn't it be acid catalyzed hydration of an terminal alkene instead? Would that be favored before this would, if it's an acid and water? I'm just wondering if that's like a big thing.
What of an alkene? What did you say it was?
Wouldn't it be like acid catalyzed hydration? Because it's a terminal.
Do
alkene.
alkenes just break in water?
And acid. I think.
Water and acid?
Yeah, and then they form an alcohol in them.
See, so if
say-
I had made any part of this example up, I'd be like, oh yeah, probably. But this example like comes directly from your slides. And my first thinking is that this bromine is on an sp3. This guy is sp3, right? It's these guys that are sp2. So this bromine as a leaving group and doing an sp2, I mean, that would require an sp3 hybridized, not an sp2. But these guys are just sort of over there. Also, there's no acid in this first step.
Okay.
We just have,
That's what-
yeah, the acid gets added here. However, we do have a double bond in our final product, even after we add acid and water. So, and according to your slides,
But wouldn't the, like, at least the stuff with the nitrogen, wouldn't that be the nitrogen be more electrophilic than a carbon. So the acid would want to go there because that's where the electrons are over a carbon.
Yes. Yeah.
I don't know about the.
Maybe. I don't know. I just usually there's not. Acid-base chemistry is so fast and so reversible that usually, like, when we're talking about like nucleophilic attack, and we can say, oh well, it could attack here or here, but let's say a Grignard reagent. There's 2 places it could attack, but like once a Grignard reagent attacks, there's no one doing it, right? And a Grignard reagent is swift and decisive, so like it attacks the, like, at whatever place is the most positively or semi-positively charged, and then you get a bond and you don't go backwards. But like, we usually don't talk that way about, oh, we've used up the acid, so this one isn't gonna, like, nothing's gonna happen over here, you know? Just because acid base is, I'll have to look that up.
I was just confused because they said an alkane on the slide and then they gave an example with an alkane.
Yeah, so I think what they mean is that we don't have this.
Okay.
We don't have a vinyl halogen. We have an alkanyl halogen, and then this is just our group. I think that's what they mean there. Yeah, that's what I'm gonna go with. So, enamines are going to be better than enolate anions for these reactions. They're less basic. Enolates are less basic, and give higher ratios of substitution to elimination or alkylation on carbon. Higher ratios of substitution to elimination products and more alkylation on carbon. So, we can do substitution, enolate, and get other stuff happening, right? Enamines, they do their thing. Like, we're not gonna have any, what am I saying? Perfect. That's what I'm saying. It's break time.